In our previous unit, we discussed how we are dealing with time and sequential logic in computing systems. What we'll do in this unit is actually talk about the actual elements, the chips that will allow us to provide this kind of functionality. So let us recall how we started the last unit, where we saw that the way we deal with time, we have integer time units. At every time unit t, we want something that can depend, whose value, to compute some kind of function, and the output, and some kind of function, and the value at the previous time unit, at time t minus 1. So what kind of element do we need in order to provide such a functionality? Well, the missing element, we need something, at the very basic point, is we need something to actually remember one bit of information, move one bit of information from time t minus 1 to time t. This is what we have missing. We have lots of combinatorial logic so far that can do any kind of manipulations that we want within a single time unit. But actually moving information from time t minus 1 to time t is something that is still missing. Now, if we look about that kind of thing in the way we're in this abstract way that we're thinking about these discrete time units, at the exact time when we switch between time unit t minus 1 to time unit t, this new element must remember the bit. At that point, it has to remember what happened previously and carry it on to the next stage. Without that, we cannot have this kind of functionality. Now, this means that at this transition point between two consecutive time units, it must have state. It must remember whether it's now remembering 0 or is it now remembering 1. That means it has to be in two different physical states in its implementation. These two physical states, it must be able to move between them according to the logic at the previous time unit, which means it needs to be able to flip between these two different physical states. And elements that can do that thing, that can change situation between two different kind of states, are called flip-flops. They flip to 0 and then can flop back to 1. And the point is that this flipping and flopping is something they remember. It's not just a function of the current input, but it's something internal to them they remember between time units. So let us view now the basic flip-flop that we will be using in this course, which is called the clocked D flip-flop. This flip-flop has a single input and a single output, and it basically remembers the input from last time unit and outputs it in the next time unit. So if we again look at the diagram of our time units and assume that our input looks like this, it starts with a value of 1 at time unit 1, goes down to 0 for time units 2 and 3, and then goes up to 1 and down to 0 again. Then when we look at what the D flip-flop will do, at any time unit, it will actually return the value that was in the input in the previous time unit. So at time 1, we don't exactly know what our output will be because we haven't specified what happened in the previous time unit. So for us, it's gray. We just don't know what the output is. But once we get to time unit 2, then we know exactly what the output needs to be. It needs to be exactly what the input was at time 1. Similarly, at time unit 3, we know it has to be 0 because that was what the input was at time 2, and so on. At every time point, we are having simply the previous signal that was fed as the input shifted one time unit to the right. And this is what the clock D flip-flop does. And this is going to be the only element that will provide all the sequential logic that we need in this course. And from this, we'll need all the kinds of sequential circuitry that we need, memories, counters, and so on. One thing that I'd like to mention at this point is the meaning of the little triangles that we see at the bottom of the D flip-flop diagram. The meaning of this is that we have a sequential chip, a chip that depends on time. As opposed to all previous chips or all combinatorial chips that we had so far, whose output only depended on their own inputs at any given point in time, here we have a chip whose output also depends on what happened previously on states that's kept inside this chip. This is the only point that we care for, this logical dependency of time, although it's probably also interesting to note that in any physical implementation of a D flip-flop, this means that the implementation will also need some kind of access to this clock that we mentioned in the last unit that actually breaks down the physical continuous time into discrete time units. Again, we won't care about this because we are living in our abstraction of discrete time, so from our point of view, this is just a way to remember that this chip has state and can remember and depends and whose output also depends on what happens in previous time units. Now at this point, let us just say one word about the implementation of a D flip-flop. In this course, we're going to deal with it as a completely primitive operation. This is something given to you that cannot be manufactured from anything else, but just you're going to use it just like you've used the NAND gate, and from D flip-flop and the NAND gate, you'll actually build everything in the course. In many other courses, you actually follow what happens in most real-life hardware. You can actually construct a flip-flop from NAND gates when you actually take the NAND gate and put them into some kind of a loop between each other. This kind of loop basically has them amplifying the same signal again and allows them to get stuck either in a 0 or 1 state. And with some additional logic, you will also be able to manipulate this state from the outside. This kind of logic usually has 2 steps. The first step is what I've just described, having this kind of cycle that allows it to somehow remember information. And the second step is to actually have some kind of logic that actually provides isolation between subsequent time units. We will not describe in this course how this is done, even though it's extremely elegant and beautiful, because we basically think it's confusing. We do not think that is the right way to think about a logical circuitry. We think that it's completely worthwhile to keep separate in your head the combinatorial logic, which happens instantaneously, and the sequential logic, which we don't want us to thinking about how it is constructed from lower levels combinatorial stuff, but rather think about it as its own primitive block. So now that we can remember one bit, from this we can build everything else. In fact, there's a generic paradigm of how we're going to build all our logic in the computer, and it's going to be a combination of remembering information via this basic D flip-flops, and then manipulating them using combinatorial logics that we built in the first 2 lectures. So in particular, the usual way we do things is we have an array of D flip-flops, which basically comprise all our memory in the system. Their output is going to be fed into some combinatorial logic together with the new input that you get in this time unit. And all of this is going to change the state that we have in the D flip-flops for the next time unit. This is a general way we're going to build everything, whether it's a memory or a counter. For example, if it's a counter, we're going to remember a number in all these flip-flops, and the combinatorial logic will basically add 1 to the counter. And this way, every time unit, the new value that we have will be 1 more than the old unit. Let us actually now look at the first bit that we're actually going to, the first device, the first chip that we're going to actually build from a D flip-flop. And this is a device that actually remembers a bit forever. So the D flip-flop provided the basic functionality of remembering a bit for 1 time unit. If we want to build a memory, we want something that you can remember a bit forever. We store it, we tell them now start remembering this bit, and then it keeps on remembering the bit. Such a device, such a chip, is defined by the following API, by the following chip that we have that we call the bit chip. It has 2 inputs, an input bit and a load bit. Once we take the load bit and put a 1 into it, we want to remember the input bit at that time. When the load bit goes down to 0, we want the chip to keep remembering the last time that the last input that was loaded into it for infinity, until a new load operation is performed. So this is basically the logic that we have. If load at time t minus 1 is 1, then we want the next out, the out at time t, to be exactly the input at time t minus 1. Otherwise, we want the output at time t to just keep on being what it is now, basically the old value that we remember, the same as out t minus 1. How can we build such a chip from our humble D flip-flop? Before we look at that, let us see what this bit chip needs to do. So again, let's look at 2 possible signals for load and for in. So for example, we asked for loading in time units 1 and time units 4. While input is, let's say, it's 1 in the first time unit and then it goes down to 0. So let's see what do we expect the output of this bit gate to be. Well, in the first time unit, we don't know the history, so we have no idea what the output is. Let's put it in gray. Now, in time unit 2, it's supposed to be, since we asked for a load at time unit 1, what we want in time unit 2 is for the output is to be exactly like the input at time unit 1. because we have a load at time 1, the value of in at time 1 is 1, the output at time 2 should be 1. Now after that, load goes down to 0 for the next 2 time units. So basically what we want is we want the same output to remain just because low is going to 0, even if input changes. So we're going to keep on maintaining the same value for the next 2 time units until load goes up to 1, and then we'll have to see what we're going to do. Now notice that for this time units, whatever input was, whether input went up or down, it does not matter. In any case, we will not change the output of our chip. Now let's see what happened at the 4th time unit. At the 4th time unit, load goes up to 1. Load goes up to 1, so now we're asking the chip to load a value again, and the value that we load is the value of in right now, which is the value at time 4, which is 0. Notice that we asked to load at time 4, but this will only affect the output at time 5, because the output at time 5 is basically changed to the input at time 4 only if load at time 4 asked it to do it. So that means that at time 5 our output will go down to 0 as planned. So this is the intended functionality of the 1-bit register. How can we do that? How can we pipe the value that we remember so it will keep on being remembered until we ask to change it? Well, here's the first naive approach. We'll take the output, what we currently remember, and let's plug it back into the input of a D flip-flop. And this way, the D flip-flop, unless we tell it to load a new value, will just keep on having the same value looping inside it, if you wish. This is a very basic, the correct idea in general, but of course this is not a real chip. How do we connect? How do we put the real input in if we want to also put the output of the D flip-flop back into itself? How is this connection done? So this doesn't quite work. We really need a way to combine these 2 possible sources into the D flip-flop. One source, which is the output from the previous stage, and another source, which is a new input. And which one of them we want to actually plug into the D flip-flop depends, of course, on whether the load bit is set or not. But we already know exactly how to combine 2 sources into one output, and this is exactly the multiplexer. So if we actually take the input and feed it into one input of the multiplexer, take the previous output and feed it into another input of the multiplexer, and then choose between them, this is exactly the correct functionality. We can actually see how that works by following step by step. So let's try to follow this implementation and see how it works real time. Again, let us take 2 possible example inputs, load and in, that we get from some other source that we don't care about, and see what our new implementation does when it's fed these 2 signals and inputs, and what it produces as output. Let us start with time step 1. At time step 1, there is one piece of information that we don't know. We don't know what the previous state of the D flip-flop was, what the previous out was, because it's not specified in this example. So for us, it's going to be a question mark. All the other bits we can complete. We know that in is 1 because that's what we see in our input. We know that load is 1 and so on. Now notice that the multiplexer here, because load is 1 and because in is 1, even though we don't know what is the input to its other input, to its lower input, we still can tell very well what the output is, what the output of the multiplexer is, and that's going to be 1. Now, we know what the input to the D flip-flop at time unit 1 is, so even though we don't know the output at this time unit, we know everything about the input. Now we can see, now this implies exactly what is going to happen in the next time step. In the next time step, the 1 that was the input of the D flip-flop is going to be passed and is going to be the output of the D flip-flop in the next time unit, exactly when we switch between time units. Now we can fill up the rest of the information about what happens in the second time unit. In the second time unit, we know what in is, that was our input, we know what load is, we have the previous out, so we can calculate exactly what the multiplexer does. And the multiplexer basically picks the previous output from the old value of the DFF. And then we know what the input to the D flip-flop is going to be. It's going to be again a 1. And this we can keep on doing step after step. At each point in time, we know the previous values, we know what load is, we know what in is, we can compute what the next situation is. And at every given point in time, we can write down the values and all the different wires, just like we did in combinatorial logic. And as we see, this implementation actually provides the required functionality, the functionality of whenever load is being pulled too high, we load the input from in and keep it until the next time that a load is asked. So at this point, we've looked at what is the basic unit that allows us to do sequential logic in a computer, and we've built the first interesting element from it, a 1-bit memory. Once we have a 1-bit memory, in the next unit, we'll actually build a whole huge memory of lots and lots of bytes and words.